start. I don't want to make the topic a little bit very boring, but I would like to, because I guess the participants are mostly faculty and research scholars, although I'm not able to see them. Yes. So the purpose of So the purpose of my talk will be mainly focusing on to introduce you to the current scenario of what we call the Eigen structure of. There are actually 4 words that are very important in our lecture, or it's not be exactly a lecture, but more of an interaction. I would appreciate. So wherever you have any difficulties or anything that you would like to clarify, you are most welcome to interact and ask. Because I don't want this to be a formal lecture kind of a thing. Only I speak and you listen. So the purpose of this is to just just handhold you into the latest problems and the latest research challenges that is actually bordering our 2 main important technologies, which are very much a part of your 5G. We all are knowing about, already we know about our 5G and the current scenario, etc. Okay, so we'll be talking about, there are 3 things we have talked about here. One is, of course, the MIMO. We all are mostly familiar with what is MIMO, at least those of us who are working in the communication areas. Massive MIMO, I think most of us know that the massive is not with respect to size, but with respect to the number of antennas that we these days have. The new thing that is coming over here, which is actually getting integrated, is my millimeter wave. So this is broadly the channel. Okay, the frequency ranges in which the new spectrum that is going to be used for communication, and the thing that is very much part of a signal processing that is actually going to be included over here. It is already included, but then it's going to play a very strong role is the Eigen structure. So we'll just have a quick look into the scenario that we have right now. So I think most of us are very much aware that these days we are talking about 5G. So in the plan of 5G, the 5G actually it was introduced back as early as 2010, so almost a decade has passed. So what is actually happening is that we all have experienced that our voice quality of our cell phones is continuously increasing. We are having better quality. And not only that, our Wi-Fi or the wireless LAN that we are using, definitely we are having a much better, higher speed, megabits per second. Okay, but this focus is now where we are all working with our smartphones. Most of the time we are associated with the smartphones, and where we are moving to the era when your smartphones will now work as your laptop. So maybe perhaps, so there the big changes already have started coming. Some countries have already implemented 5G, and also we are also into the way of it. So the 5G wireless system, please note the frequency range in which the current 5G is working. It is between 1 to 100 gigahertz. And the important point over here is that different properties of this band, because you can see it's a huge range, 1 to 100 gigahertz range in which the 5G is expected to operate. So there are some bands, low frequency bands near about 1 gigahertz. They will be mostly used for cases which need wide coverage, and the higher bands towards the higher side above 24 gigahertz, they are being planned for using where we require more, the focus is more on getting larger bits per second or larger throughput. Okay, and large of course we need a large bandwidth for it. So there is, because what happens is that the properties of the frequency spectrum or the channel is totally different in this entire range. Incidentally, the spectrum provided by our unlicensed 60 gigahertz, now although our Wi-Fi etc., they are working in the 2.4 gigahertz range, but when we move to the higher unlicensed bands, 60 gigahertz and all, so there almost more than 10-fold increase of bandwidth is we are expected beyond the 4G. So right from our engineering days, I think we already have studied there are mainly 2 scarce parameters. Okay, that earlier we were talking about power limited system and bandwidth limited system. Then normally there's a trade-off that if you try to save power, you have to spend bandwidth. If you try to save bandwidth, you have to spend power. So there's a trade-off between power efficiency and bandwidth efficiency in general for most of our modulation systems or communication systems. It's a general fundamental trade-off. Incidentally, in today's world, in today's wireless scenario, both are becoming scarce commodity. Okay, earlier it was bandwidth is as such scarce, but now we are also constrained with power. Why with power? Because power once, of course, I mean, for the purpose of green communication, we definitely need to save power. But then there are 3 important points that I've tried to sum up over here. First of all, that the transmit power cannot exceed. We know that due to the radiation hazards, people are saying that we have to go limit the amount of power that we can actually be exposed to. Then, if you go on increasing the power, what happens is that the sensitivity of the linearity of the receivers beyond a certain the range of power is very difficult and costly. So here the power limitation is coming. Second is that the frequency spectrum, as we already know, is a very scarce and expensive commodity, and this makes us very difficult to increase the bandwidth. So now we are sort of stuck up. Neither can we increase the power, neither can we increase the bandwidth. So, and then we know that by Shannon's law, you cannot have the capacity, cannot increase unless you increase one or both of them. Okay. So new techniques have to be introduced to realize the needs of the modern wireless systems. At the same time, we need to be green, we need to save energy. So the problems are challenges are now of a different nature. Now, there are three important things. This is a very important formula I've tried to take put before you. This is a very highly relevant formula these days when we are designing a cellular network or wireless network. There are three factors. We call it B multiplied by D multiplied by B stands for the bandwidth, definitely. We need area throughput. So you see, the area throughput is what we are trying to actually have the parameter. So bandwidth, D is the number of cells that you are able to accommodate within a given area. So cells, number of cells per meter square. And SE is definitely my spectral efficiency that is achievable in every cell. So overall, this is the area throughput that we need to maximize. Okay. So now here, what we try to do, the overall approach is that we try to break it into three parts. So maybe when we are going for 5G, we are trying to have an expansion of, so individually we try to have an expansion of, let us say, even 10 times in the bandwidth. Cell size. So if you are accommodating more number of cells, I think all of you must have been studying about the concept of small cells. We are moving from macro cell to micro cell to femto cell to pico cell. The size of the cell is decreasing. The moment the size of the cell is decreasing, the number of cells that you can accommodate becomes more. So D is the second parameter that we need to actually, this is a multiplier, another factor that we are trying to increase maybe 10 times. So, and of course, spectral efficiency. There are different ways of improving the spectral efficiency. So individually, if you are able to improve all the three, you get almost number of, the capacity increases almost 1,000 folds. So this is the approach that we normally want to use. Also, it is to be noted that the lower frequency bands, as I told you, lower frequency bands have got an advantage that they are able to propagate to a much greater distance, but they will offer you slower data speed. So once again, you have a trade-off. If you use the higher frequency band, they are going to cover smallage area, but they will carry much more data. So as I was telling, my original, this thing is almost from 5G is from 1 to 100 gigahertz. So we have to make this kind of a choice. Second thing, the three approaches that we were talking about, increasing B, D, and spectral efficiency, the three approaches that we were talking about. So first is definitely we talked about the densification of the cells. That means accommodating more number of cells per unit area. Second, increased bandwidth. This is where my millimeter wave will come into picture. The moment we go for the millimeter wave, it is going to increase this particular factor. The bandwidth factor. Okay, because millimeter wave means the frequencies, the wavelength is of the range of millimeters, and you have a much higher frequency range available, and also the bandwidth. Okay. So also by making the better use of the Wi-Fi's unlicensed spectrum in the 5 gigahertz band. Now we are trying to move from the Wi-Fi's, the wireless network that we are operating, we are trying to move into the much higher band. Okay, 2.4 to 5 till higher band. Second, the third factor that we are talking about is spectral efficiency. Now, this is where spectral efficiency can give us a huge difference to the MIMO can give us a huge difference to the spectral efficiency that you can achieve. Now, when we try to use massive MIMO in millimeter wave band, so that means when I'm getting the advantage of both spectral efficiency as well as bandwidth. Okay, so when we use both? So, but there will be some problems, there will be some benefits. That is what we are going to basically see. What are the challenges in forthcoming towards us when we are trying to move to massive MIMO. So massive MIMO is basically when I'm using a large number of, I think MIMO, we all know that you use a large number of antennas on the transmitter and a large number of antennas on the receiver. Now, when that number becomes very large, that becomes a massive MIMO. Okay, so are we okay till now? So can we move further? So this is the next thing that I think we all know this famous equation. This is my Shannon's Shannon's channel capacity equation. So when we take the bandwidth per hertz, when we take it per hertz, then we have, this is the B log to 1 plus SNR. Okay, so the spectral efficiency is bandwidth, I mean bits per second per hertz. So for every hertz, log to 1 plus SNR. So obviously we understand that to increase capacity, either you increase the power or we increase the bandwidth. Bandwidth is a big no-no. You cannot increase the bandwidth. So one way you can go is that if we go for millimeter wave bands, we are increasing the bandwidth. Okay, but that is one aspect. Second is how to improve the SNR. Improving SNR is normally we know that you can improve the SNR by increasing the signal power, but then we cannot increase the power. Okay, so one way is definitely if you increase the power, your SNR will increase. But the current coding techniques, I mean, I'm talking about the channel coding techniques. So whatever channel coding techniques you have, we have already reached the theoretical Shannon limit. I think in our DTech days, most of you must have studied about the Shannon limit. Okay, that beyond that limit we cannot go. So already we have reached by most of our channel coding techniques. You know, we have very powerful techniques, trellis coded modulation and almost all the good channel codes. They give you almost a, you cannot go beyond that capacity. Now, when I've gone beyond, how to go beyond that capacity? Now, there is no way of doing anything else. So, the only way that can happen is that, because if you now, as I was telling you, that you cannot increase power, bandwidth is already over. Now, here comes the role of multiple antennas. The moment I have multiple antennas at the transmitter and receiver, there are some opportunities where you can get array gain, diversity gain, interference suppression, and multiplexing gain. There are 4 types of functionalities that can achieve by a MIMO system. Please note that all these advantages you can get without increasing the power. So that is the takeaway from the most important takeaway for MIMO systems, that without using the same power and same bandwidth, okay, simply by increasing the number of antennas, you are going to get a lot of advantages. Okay, only thing is that you must know about the channel, because how are we doing it? The basic idea of doing it is to do some signal processing. So what we do is that it is something like a signal processing that we do. At the expense of some signal processing, we are able to get so many gains and so many advantages without having to spend anything additional on the power or bandwidth. That is the most important takeaway from MIMO systems. But only thing is that you have to do some extra signal processing, and that signal processing can be done only when you have a good knowledge of the channel. Okay, which the transmitter must know something about the channel. Okay. So, for example, just to give you an idea, if you have a 4x2 MIMO, that means if you have 4 transmitting antenna and 2 receiving antenna, so on an average, and if you know the channel, okay, we'll come to, because we have methods of estimating the channel at the receiver, and this channel, there is a way of actually sending the information of the channel back to the transmitter. We call this as a closed loop feedback system. So the transmitter has the knowledge of the channel, and then if you have the knowledge of the channel, then typically the amount of, you can almost double the capacity as at -5 dB. Just see the low SNR. Even at SNR as low as -5 dB, you can double the capacity. Similarly, for a relatively higher SNR +5 dB, you can add almost 1.5 bits per second per hertz. So depending, so if your bandwidth is 100 hertz, so multiplied by 100. So that is the rate at which you can actually, if your bandwidth is of the order of a few megahertz and gigahertz, you can easily imagine the amount of capacity increase that you can get when you are using a MIMO system. Okay. Now what is so special about the MIMO? Whenever I'm using many antennas, okay, instead of one antenna, I'm using many antennas. What happens when you use a MIMO? So the most important thing that you'll see is that when we use MIMO is that it can turn the multipath beneficial. That means, you can turn the multipath beneficial. Here, multipath beneficial means normally multipath fading is a strong disadvantage of any wireless system. But here, this is one system where multipath is actually going to be made beneficial. Okay, so channel fading is no longer a disadvantage. Rather, MIMO is actually making use of the channel fading rather than trying to compensate for it. Okay, so normally there are, as I told you, there are broadly 2 aspects of MIMO. You can get, we normally try to get diversity. Do you know the meaning of diversity? Diversity is when you use the same signal is transmitted in more than one domain. Okay, so maybe in the time domain, in the frequency domain, or in the space domain. So in MIMO system, you are using, instead of sending the signal between one pair of antennas, you are sending the same signal to multiple pairs. Now this is not, now this is just taking a chance that when I'm sending, let us say I'm sending many, instead of sending, sometimes you are not sure of whether something will reach or not. So if I just send 5 signals, so one of them is definitely going to reach. So the biggest point of MIMO is that if your channel is in deep fade, we still see you have advantage in both the cases. If your channel is in deep fade, you can always use diversity and try to get the benefit out of it. And you get a diversity gain, you can get a good amount of diversity gain. And this will improve the quality of your signal. The reliability of your communication link will be excellent. Okay, it will be improving. If the signal is not in fade, that means you have a channel is reasonably good enough. Then what we do is we do spatial multiplexing. What is spatial multiplexing? Spatial multiplexing is where you get the capacity multiplication. You can double the capacity, triple the capacity. Okay, you can almost increase the capacity to whatever amount you want with the help of little bit of signal processing and the use of multiple antennas. Once again, I strongly repeat that you are not spending any power or bandwidth. So what are we spending? We are simply spending some little bit of cost on the antenna system, and that antenna has to be properly designed, and they have to have a proper what you call pre-coding. That's what we will be studying, which is related to the Eigen structure of the channel. So what in very simple words, that the transmitter as well as the receiver both must be very well be knowing what is the type of channel. Okay, it is something I typically give an example of, something like, if you already see, suppose you are trying to, I just give a very simple example to my students sometimes. So suppose you want to travel to a new city, you want to come to let us say Dhanbad, you are coming from a different city, you don't know anything about Dhanbad. So what happens that, what do you normally do? You normally can ask any of your friend, or you can even ask me or something like that. Suppose I'm taking a train from Rourkela to Dhanbad, so, or if I'm doing a car journey by a 4-wheeler and coming. So what do you think will be the problems? So now I give you the feedback. See, you don't take this particular road. This particular road is bad. Okay, you have lots of, the road is very bad. So it's better you come through Bokaro road or some other road. That road is good. You will take less time. Or there is too much traffic jam on this part. Then you take a bypass road. So what is happening? You are basically taking feedback from me before coming to Dhanbad. Okay. So before making the travel, you are already aware of the path. And already I tell you, okay, you don't stop for food at this place, and you will get a good restaurant at this place, and you will not get water in between, so you carry your water. So whatever is the problems of the journey, I tell you beforehand. So you are already prepared. So when you make the journey, you are already prepared. You have already taken the corrective actions of the problems, and then you start your journey. So naturally, you are not going to face the problems. So this is exactly the principle of what happens in MIMO. Okay, because they have the knowledge, the transmitter already has the knowledge of the channel. So what it does is that it does some signal processing, and then beforehand it tries to compensate so that by the time the signal reaches, it is not going to be affected by the problems of the channel. So this is what I mean by knowing the structure of the channel. A little bit of signal processing if we do, you can get it. Okay, so transmit power from base stations and terminals can be scaled down to pursue energy gain. So what happens is that, so what happens is that you can actually plan out your signal. So okay, I'm not going to, what will be your power, what will be your modulation, and the entire thing can be planned very well. Okay, so this is basically the theme. Otherwise, normally MIMO systems, as I told you earlier, there are 2 broad aspects in which you can actually study them. This is my diversity scheme and my multiplexing scheme. Okay, diversity scheme, and please note that in diversity scheme, can you see in this particular diagram, can you note the difference between diversity, MIMO with diversity? This is MIMO with spatial multiplexing. The main difference is that when I'm using in the diversity scheme, it is improving reliability. The same bit stream is given in all the antennas. Whereas in spatial multiplexing, you give separate it into three. Suppose there are 3 bits, so one first bit goes to the first antenna, the second bit goes to the second, and third one. So basically there are 3 layers in which you are going to separate. And the next 3 bits, again the 4th bit will go into the first antenna, 5th bit will go over here. So this is what happens. This basically increases your data rate. Normally there is a trade-off. You cannot get both. So either you get a diversity gain or you get a multiplexing gain. Okay. Now you have to sometimes you optimize. It's better. So some MIMO schemes are diversity schemes. Some they use multiplexing schemes depending on your application. And one thing, the spectral efficiency, one important, I mean, those of you who have studied MIMO, is the most important thing that this figure you must have seen in any books or papers, that with respect to the number of antennas, there is a linear increase in the capacity. Please note this side y-axis is my spectral efficiency. And this is my SNR. Okay, EV by N0 is my SNR. Okay, so with as SNR, SNR increases, definitely the capacity increases, but look at the linearity increases. M equal to 1. M equal to 4, M equal to 8, M equal to 16. So for the same SNR, can you see the huge difference in the capacity? The linear, but please note that for this particular scheme to work, the channel has to be perfectly known at the receiver. And once the channel is known at the receiver, it sends the information of the channel to the transmitter. And then what happens, the situation is that both the transmitter and the receiver knows the channel. And knowing the channel, these advantages can be affected. So we were talking about a very simple example that we call it Eigen mode transmission. We'll come to what we mean by Eigen mode transmission. Eigen, I think all of us know the eigenvalue decomposition. I think in our linear algebra mathematics classes and in our engineering courses, we must have studied at some point that you can always find, I mean, for any matrix, you can always find eigenvalues and eigenvectors. So similarly, so we they are orthogonal. You can they are, I think the eigenvectors that you find, they are orthogonal, and if you multiply them, it is actually a scaling transformation between the matrix. This is a linear algebra. We already have an idea about the what we call the eigenvalue decomposition. We'll see how it is used in MIMO. Here in this particular slide, we will introduce you to what is called the pre-coding scenario in MIMO. This is the most important signal processing happening in MIMO that is giving you so much power. What is pre-coding? Pre-coding, as I was telling you the simple example, that before transmitting only, you are already aware of the channel and you are doing some sort of coding which is able to cancel the effect of the channel. For example, sorry, Rajini, I'm in a class. I'll just call you afterwards. I'm in a class. Okay, so this is what happens, can you see? So this is my antenna. So you have this is one channel, H1 e to the power j51, e to the power j52. Now what happens is that we all know that in multipath, what happens when it reaches the receiver, a destructive addition may happen. Okay, and that is why you have the fading. Now what we can do is, please see what we are doing. Before transmitting only, we are multiplying the signal, this X signal. We are multiplying it with e to the power minus j5 because we already have the knowledge of the phase shift that is going to be introduced by the channel. So what I do is I just multiply it with e to the power minus j5. So what happens? This is the corrective action I'm taking because I already know the value of phi1 and I know that this particular channel is going to introduce a phase shift of phi1. So I just multiply it with minus phi1. So what happens? At the receiver, they get added. So this is basically the very crude way, if you try to understand what is happening in pre-coding, is that the transmit signals are pre-conditioned to match the channel so that they will add constructively at the receiver. Okay, is it clear? Any questions? Any questions till now? Yes? Do we go ahead? Okay. So here, basically, so this is just an example. Can you see? So suppose we have a MIMO channel. So there are suppose 4 paths. Okay, it's a 2 cross 2. So you can see typically if we try to measure the signal, so you can see the channel. This is suppose 1 1. The antenna. This is 1 1. This is 1 2. This is 2 1. This is 2 2. Suppose we have a 2 cross 2 MIMO. So you can see the signal strength with respect to time is all different. So for example, this particular at a given instant, for example, at t equal to 10, this particular antenna is having excellent signal. This is also having excellent. This is also having excellent. only this particular antenna path is going to have a pure signal. So what the basic idea is that the probability of all the paths going into fade simultaneously is very less. So that is exactly when, and we do some proper combining, so that will give us the diversity. So normally it's done is that we need to find out, so this is a, so we need to find out what we call the channel matrix. So if suppose it's a 3 cross 3 channel, so there will be 3 transmitting antenna and 3 receiving antenna. So in a general case, what do? We send signal only through the first antenna and then try to receive what it was. So when I'm sending this red one, the first one, I'm getting 0.2 minus 0.1 and 0.1. I try to measure the signal received at all the 3 receiving antenna. Similarly, I send transmitting signal. I don't send anything with the others. So in the second case, I send signal only through the second one. I get this blue one, okay? I get all these 3 readings at the receiving antenna. The third case, I just send the signal only through the third antenna and I get this, the 3. So do you see, this is my channel matrix form. So if I have a 3 cross 3, so basically I'll be having a 3 cross 3 channel matrix. So usually what happens is that your first step is to find out the channel matrix. So this is the basic step that we start with. So channel matrix could be real, it could also be complex coefficients, okay? Because individually they could be all Rayleigh coefficients. So this is typically a 3 cross 3 will look something like this or this, something like this, okay? So now this channel is changing instantaneously. So we need to estimate the channel at frequent intervals. Okay, now what happens is that you have, this is my channel matrix. So normally the number of rows is the number of receiving antennas and number of columns is the number of transmitting antennas. So you have NT cross NR cross NT, NR cross NT. Okay, so basically you have the simple. What happens is that the first and the total power, and you see the total power. So suppose the transmit power of each transmitter is 1, or it could be just multiplied by this. This is a very simple equation that we have. And you see the total power is actually divided into the so many number of antennas. And individually the total power is divided. Suppose there are 5 number of antennas. It's a 5 cross 5 system. So it is going to be divided amongst the 5 antennas. And then it is going to be transmitted to the receiving side. Receiving side is having, let us say, another 5 antennas, or whatever is the number. So accordingly, every receiver, the first receiver is going to have a signal H11S. This is the channel coefficient of the first one, H11, H12, and so on. So basically, you have so many number of equations. Okay, now if the number of equations is larger than the number of unknowns, that means if NR is greater than NT, then you can always find out a compact solution by using a zero forcing algorithm. Zero forcing algorithm is nothing but when I just invert this matrix. Okay, so H inverse, if you find out H inverse, you should be able to get back your original transmitted signal, okay, from R. So S is as a matrix notation, your S will be H inverse of R. So now this is possible only when NR is greater than NT. But what happens when NT is equal to NR? Then the solution can be found out. As long as it is less than or this, you can always find out by inverting the matrix. Normally, NR is equal to NT. Okay. Now, what happens is that in the case of MIMO, when we are moving to massive MIMO, what happens is the number of antennas is huge. Earlier, we were working with 2, 3, 4, 5, but now when we are going for massive MIMO, can we increase this number to tens and hundreds? What happens when you have such hundreds of antenna? The entire matrices becomes just numbers like random. These are all random entries depending on the channel coefficients. So working with this theoretical analysis of this random matrix, we do use random matrix theory, and theoretical analysis becomes very challengeable. And most of the analysis you'll find in papers and all, they do it through Monte Carlo simulations. It's massive MIMO. So now that these are, I'm just trying to now get into the problems or the research challenges that you have in massive MIMO. Otherwise, this is the normal MIMO system. Only thing is that the number increases. But then what is the problem when you increase? Or what is the way out? The way out that we were talking about is to know the channel. This is my channel. Now, this is a very complex matrix to handle with, as I told you. So one way is that what we do is, this is where my signal processing can help. So a very simple SBA, what we call dual decomposition. This is also a very similar to your eigenvalue decomposition. Only thing is that in eigenvalue decomposition, the matrix has to be a square. And in singular value decomposition, SVD that is called, the matrix can be a rectangular. So what is done is that this channel matrix is factorized into 3 matrices. This is U, sigma, and V. This is basically, you break down this. There is a way of doing it, SVD, similar to your, eigenvalue decomposition. You can also use SVD. And most of the softwares, including MATLAB and all, they have the functions available to do the SVD. So once we have the channel matrix is N cross NT. Please note that its rank of the matrix is very important. The rank will usually be less than or equal to L, where L is the minimum value of NT or NR. So if it is a 5 cross 2 system, okay, so your L will be equal to 2, the minimum value amongst the 2. Okay, so if the rank of the matrix that you get is less than this, okay, then there will always, you can find out 3 matrices. So this matrix factorization we can do. Okay, so you can just go through it. Those of you are not familiar, you can just have a quick, this is very simple to understand. Okay, if you know it, then it's fine. Okay, that how to do the singular value decomposition. This is the first and this is the most important step of studying a MIMO channel or designing it. So I have to know the channel. The moment I know the channel, I factorize it. So you get U matrix and V matrix. So for example, if I have a 3 cross 2 MIMO channel, so I can break it into 2. So what will happen is that you will have, this is 3 cross 2. So this matrix, a channel matrix, and this you will get a center matrix will be of the same order as this. Okay, you can easily check. And these 2 matrices will be all square matrices, or they will be orthogonal to each other. You will get what you call the singular values. So here corresponding to, because as I told you, the number of receiving antennas is more than the number of transmitting antennas. So the minimum of NT and NR is 2. So you will get basically 2 singular values. Okay. So this is straightforward mathematics. So this is what helps us. These are our unitary matrices and orthogonal matrices. Now what we do is, please note that this center matrix has got the same structure as this. Okay, and this one, the center matrix is always be a diagonal matrix. If it is a square, this will be a perfectly diagonal. All the other elements will be 0. Now let us see what happens when you have this diagonal matrix. So what we do is that using this diagonal, this center matrix, and using these 3 matrices. So please note what is happening practically in the MIMO system. Okay, I send a pilot carrier signal. With the help of the pilot signal, the channel is estimated. Once the channel is estimated, the channel factorization will be done at the receiver. Now the receiver knows all these 3 matrices. They will send the value of all these 3 matrices to the transmitter. So the transmitter and the receiver both know the matrices U, sigma, and V. Now look what happens. What we do is that in this transmitter side, we use the, please note, I repeat, we are using the V matrix. Okay, we use the V matrix in the sender side for pre-coding. And in the receiver side, I use the U matrix. Okay. So what happens is that when I'm using the U matrix over here in the pre-code, so what I do is that the original signal is first undergoing some pre-coding. So what is actually happening is that you basically counteract the effect of this U. So whenever you are multiplying here with a U star, U transpose, so this is identity matrix. Similarly, here this is V star. So you do receiver may you do U. So the U is, are you getting it? So I use V multiplication over here and U multiplication over here. So this V gets multiplied with U, and again you have a U over here. So totally what will happen is that these 2 matrices will become unitary and you will be left with only this matrix. That is exactly what happens. A very interesting mathematics happens over here. Okay. So for example, I just take an example. Suppose this is my regional channel. Okay, I do the singular value decomposition. Look, I get 3 matrices. Okay, I get 3 matrices. Note this is a 3 cross 3 matrix, so I'll get 3 diagonal values. Okay, so these are known as the singular values. So what happens is that now entire channel now becomes like a simple independent channel. Earlier, what happens was that your channel matrix was a entire 3 cross 3. You have H12 and H21. Whenever I have some finite value of H12 and H21, that means there is a correlation between path number 1, antenna number 1 and antenna number 2. Similarly, 2, 3, 3, 2. Now, what is happening in the center matrix that when you take the SVD, this matrix is getting This matrix is getting just a diagonal matrix. So what happens is that it's simple. Can you see your original equation was here? Can you see my original equation was R1 was H11S, this. What will happen? All these values will become 0, H12L. So what will be your equation? Your equation will be R1 equal to H11S, R2 will be equal to H22S, R3 will be equal to H. So you'll have just very simple equation. Entire thing becomes just like a parallel stream. Okay, so what happens is that this process of SVD, this is exactly known as the Eigen structure of the channel. So what we do is that we study the Eigen structure of the channel, derive its singular value decomposition, and you effectively have 3 independent channels. The channel gains can be, you can design the entire system with channel gain of these singular values. So this entire thing equivalent becomes, so please note I'm multiplying, this is my pre-coding. See, I pre-code in the transmitter and I do some processing in the receiver. Look what I'm doing in the pre-code. I'm multiplying it with V. What is V? V is this. Okay, please note that this V matrix I'm using in the transmitter side, whereas the U matrix I'm using in the receiver side. Now, please, if you multiply it with this U sigma V, so what will happen? With V and you have VH star, okay, you have V and V star. So that will become one identity matrix, and you are multiplying over here. So you're compensating the effect of this U with at the receiver. Okay, I have these, and then this V at the transmitter. So if you continuously, if all the matrix get multiplied, this is something like the compensating that we are doing. This is called the pre-coding. Pre-coding at the transmitter and what you call receiver processing, combining at the receiver. So just using this U matrix, this and this, you can just verify also using MATLAB that if you do this, what happens is that, can you see now this becomes simple Gaussian channel. So your entire MIMO channel 3 cross 3 has been now reduced to 3 independent parallel channels. Independent, not only independent there, because these vectors, you can test these vectors will be all orthogonal. Okay, you can test the magnitude will be 1 and you can test the vectors as these columns will be all vectors. This matrix and this matrix, they'll be all unitary orthogonal vectors. So as a result, this is an excellent mathematical processing that we are doing. So what happens is that the entire thing will make us 3 independent orthogonal channels. So they will not interfere with each other. But then you get a very good values also. Can you see the singular values? Normally the first one will be the highest and it is gradually reducing. Okay, in basic SVD, as we was telling, see the diagonal matrix, always your sigma 1 will be greater than sigma 2, greater than sigma 3. Normally that is how it is arranged. So what happens is that you also get to design what will be the nature of the channels. So now these 2 systems become equivalent. So your work has become very easy to design. So it is as if I have got 3 independent parallel channels. I know the channel gain is 1.4, 0.54 and 0.34. So these are just become simple AWGN channel. Okay, your Rayleigh fading channel. So input signal will be first multiplied by V and the output signal will be multiplied by the inverse of the U. So as a result, now V and U inverse, already you have in the equation U and V transpose. So what will happen is that all the 4 matrices will multiply and what remains is only this diagonal matrix. Okay, so that is the power of my Eigen structure of the channel that we try to use. See, you are trying to interpret the channel to be equivalent to this particular channel. Okay, so this is what happens. So you have the modulated symbol. So in the modulated symbol, what we please note that V matrix and multiplying over here, then it's normally going to the channel. Why is it? This H is going to be complex. Okay, it's going to be 3 cross 3, 5 cross 3, whatever it is. If it is a whatever is the number of antennas here. But effectively, what happens is that this H is equal to, if you do U sigma VH, so effectively I get a Y is equal to sigma X plus N. This is simply an additive Gaussian noise channel. So parallelly, as if look at this. This is a 3 cross 3. This was a complex MIMO system. This becomes equivalent to 3. As if 3, this antenna is going to this is going to this side. This is equivalent to this. Are you getting it? So this is called the channel decomposition. You do the transmitter pre-coding. This is called transmitter pre-coding. That means you multiply this with V, and receiver shaping means I multiply the whatever received signal you get from the channel. This is my channel. Okay, this is my transmitter. This is my channel. This is my receiver. Whatever channel I get, I simply you multiply this with U. How did you get all this? By SVD of this. Is it clear or anything you want me to explain once again? Yes, students and whoever participants, please. Anybody has any questions till now? Yes, any questions? Are you able to unmute yourself?
Yes, ma'am. Could you, ma'am,
Okay, do
demonstrate?
we have any questions or do we move ahead?
Ma'am, am I audible?
Hello?
Ma'am, am I audible?
Very faintly. Can you be little loud?
Yeah, ma'am, my question is if you could demonstrate one example of the
Hello,
Monte Carlo.
I cannot hear you. Can you hear me?
Ma'am,
Yes.
could you demonstrate?
Ifra Alam, you had any question?
Am I audible, ma'am?
A little bit. Can you be a little bit louder?
Yeah, ma'am. Could you, ma'am, give one example of the Monte Carlo simulation? Like, what will be the scenario there in terms of the NT and NR and like some
Monte
example?
Carlo simulation. Monte Carlo simulation will depend on the system model. Okay. Monte Carlo simulation, we suppose you are wanting to say, first of all, the system model has to be implemented. Okay, so the system model means, see, as far as you are doing, so when you are working with the channel matrix to be less, I suppose it's only 3 cross 3, 5 cross 5, because you have to estimate the channel, isn't it? Estimating the channel means you have to do the inverse. You have to find out H inverse, isn't it? So that is one way. The moment you try to find out, as long as if it is in a massive MIMO, then it's not going to be very difficult. Then what happens is that you have to find out Monte Carlo simulations. You have to do it. That's what I'm saying. If you do because for massive MIMO, that is one of the biggest challenges. That is one of the biggest challenges that where your, suppose you're trying to find out the bit array. Which is basically you're doing the capacity analysis. It depends on what you're basically doing. Na? So that will decide your Monte Carlo simulation. You're finding out the BER or you're finding out the capacity. So accordingly, now what we normally do is that for simulation purposes, we try to study the trend, okay, with a given number. The moment you try to increase the number, definitely you will have to spend more time on the simulation time to go for different platforms. Okay, so we'll see the main problem. That is why we are talking about the Eigen structure of the channel, because see, that is one way of simplifying the channel, because I don't need, that is exactly why I'm trying to say this, that you don't need to work with so even if you have there'll be something like a simple linear equation. So even if the order of this is 100 cross 100, okay, if I do the Eigen structure, you will find that the number of singular values is only 5 or 6. So automatically your number of equations also, the entire channel becomes simple. So now you can simulate the Monte Carlo simulation also will be faster. Otherwise, there's no point. That is why the Eigen decomposition is very important. Okay, that will help you to reduce your Monte Carlo simulation time also. Okay, am I able to answer your query?
Yes, ma'am. Ma'am, just one question that for this, whenever we go for this option, what will be the relation between NT and NR? I mean, NT can be greater than NR, equal to NR, less than.
It can be anything. See, even if NT, I told you, na, ultimately, even if you are using 100 cross 2, so the minimum of the 2 is governing it. The rank of this thing, it's only one. Your gain will be not more than 2. Okay, it is a minimum of NT cross of the NT and NR. If I'm going to get the what you call the multiplexing gain, I'm coming to that slide. Okay, I'm coming to that slide. The degrees of freedom will always depend on the minimum NT and NR, may whichever is less. Okay, so there's no point in having a 50 cross 2 MIMO system. It's not going to be very effective. But what happens is that sometimes it is very difficult to have antennas at the receiver. Rather, what we do is that we are coming to it. In massive MIMO, what we do is that we try to have more number of antennas on the what you call the base station. And then users, we try to, every user is having a single antenna, but we treat it as a single unit, multi-user MIMO. We are coming to it. I have it in my presentation. Okay, so this part is very, yes. Any other question? So this is a very important takeaway that you are able to, so let us just understand that we are able to, this crisscross thing goes away and the things become simpler. Then if you do the SVD, as I was telling you, see, for example, if you see the singular values, first one is 1.4, 0.53, then this is 0.33. Now, if you choose to ignore this, so it becomes only 2. So the degree of freedom becomes only 2. So this is the advantage of going for this. I need not be taking the entire, I don't need to do the inverse matrix inverse. They simply become independent equations and very simple to decode also. This is just a AWGN channel. Okay, this is the I mean the power of the eigenstructure. In MIMO system, the fading channel between each of the transmit receive pair can be modeled. Now, although it is a MIMO system, it becomes suppose it's a 5x5 MIMO system, that becomes equivalent to 5 CISO systems, simple 5 CISO system. That then it becomes easy for you to analyze it. The transmitter knows that the N channels can therefore allocate power. This is one of the most important application of this eigenstructure, that you are able to allocate the power to the antenna. See, suppose you are having a 5x5 antenna system, then and you have a total power of 5 watts. Now your intuition would be to divide 1 watt, 1 watt, 1 watt to all the 5 antennas. No, that should not be the case, because what happens is that if you know the eigenstructure, you can, using the eigenstructure, you can actually intelligently, you can allocate power to the antennas. So maybe one of the antennas you will give more power, the second antenna you will give a little bit less power. How much power to give? This is an optimization problem. That how to allocate the power. This is possible only if you know the eigenstructure of the channel. Okay? The transmitter knows the N channels, and the intelligent allocation of power for maximizing capacity will be very, very much essential. Okay. So rank of the matrix. This is another important thing. The rank of the matrix is N. Then the MIMO channel can be decomposed into N parallel spatial channels. Now the rank of the matrix will be decided by, as your question is answered over here. If the whichever is less, NT and NR. So if it is a 5x3 system, so 5x3 system, the rank of the matrix cannot be 5. No, the rank of the matrix has to be 3 or less. Okay, so naturally that decides the how many channels. The SVD is used instead of the, this is one point, please note that singular value decomposition is used instead of eigenvalue decomposition. Okay, but then this is the power of the entire thing. So what is important is if you undertake any study on a MIMO system, you have to see what is the kind of pre-coding. There are other pre-coding techniques also, but most of them they need the, and one of the most powerful way of doing it is through the SVD, okay, singular value decomposition. So when you do SVD, these are some of the takeaways from it, that you can send more power over the better channels. Okay, it is something like why do you waste some power on the channel which is already going to be badly affected by a deep fade. But then what we do is that it's not that we don't use that channel. Okay, as I told you, the basic idea of MIMO is that we are trying to use the multipaths rather than discard, because there's something or the other will be there in all the paths. Okay, so we try to take all the paths together, and with little bit of signal processing at the transmitter end, we are able to have a very good control over this uncertain channel, this complex channel. And you can imagine what happens in massive MIMO, and then the channel is becoming more complex. Number of principal components is the number of singular values. It is a measure of the maximum degree of diversity that can be realized. Your questions is also answered over here. Okay, that number of eigenvalues. Suppose the one of the eigenvalue is 0.00006. So naturally you can discard all those eigenvalues, and suppose effectively only 3 or 4 are there. So even if your system is 10 cross 10, but you'll find that the number of eigenvalues that are having good values. Okay, otherwise the rest of the eigenvalues are very small. So you can define a threshold that less than 0.01 I can ignore. So what happens is that you will find that although my system is a 50 cross 50 massive MIMO, but actually the number of eigenvalues is only 10. So effectively the diversity gain will be only of the order of 10 only. You cannot get the advantage of 50. But then this is where your so many things have to be designed. Okay, let us see what are the other issues. So you can elimination of interference at every antenna. Okay, then the correlation, although because see, whenever I'm having a cross correlation between antenna 1 and antenna 2, excuse me. But then what happens is that you can able to the final center matrix after SVD that you are getting. Diagonal matrix. So now these two, 1, 2 and 2, 1, this is 0. So now you are basically able to change a correlated channel into an uncorrelated one. That is why you have independent channel. Okay, it's straightforward mathematics, but it is tremendously powerful. Okay, so the gain is the singular value of the channel matrix. This slide that I showed you, yeah. So this, for example, my singular value is 1.4. This is nothing but the channel gain is, for this particular channel, the channel gain is 1.4. So it becomes very easy to interpret the channel and design it once we do the SVD. And please note that the final signal that you normally do as a pre-coding vector. So WISI. So there's a pre-coding vector where you have the coefficients. So you have I is equal to 1 to k. What is k? K is the number of. Yes. Here k, m is the number of. M is an m-dimensional pre-coding vector is assigned to different users. Okay. So the number of receivers, and k is the number of signals that you are transmitting. Okay. So if m is the massive MIMO usually means that m is much greater than k. Okay. What happens in massive MIMO is that you use base station may you use an antenna array, and then you have a large number of users. I'm coming to massive MIMO. Massive MIMO may the number of receiver antenna, number of receiving antenna is much larger than this k. Let us see what happens. So the two important channel matrix, the rank of the channel matrix. So although your channel matrix could be 5 cross 5, but the rank is 3, rank could be 4, rank could be 5 also. So it depends the rank of the channel. What happens if the rank of the channel matrix is less? So even if you have a 100 cross 100 MIMO, so you first see the channel and try to see the rank of the matrix. So the rank of the matrix is usually less. That is what happens in millimeter wave MIMO. Okay, the rank of the matrix becomes very less. Sparse matrix, it becomes a sparse matrix. Now they affect my entire design. They affect all the parameters, the capacity, the DER, the spectral efficiency, diversity, everything related to MIMO will be affected by the rank of the channel matrix. And how do you get the rank of the channel matrix? Once again, the Eigen structure helps us, because Eigen structure, as I told you, here, suppose this value was 0.003. Suppose, I'm just for an example, you take the SVD and this comes as 0.003. So 0.003 is much less than 0.5, so you can easily ignore. So that means my rank will be 2. Although my matrix is 3 cross 3, the rank will be 2. So that basically decides a lot of things. Okay, the rank of the matrix. So channel state matrix, we call it, can provide the information to determine whether spatial multiplexing is possible for multi-layer data. Multi-layer data means, suppose this is called multi-layer. It is multi-layer, isn't it? It is as if in 3 layers the transmission is happening. You are actually sending this thing through 3 antennas, and this is the crisscross channel. But this is the 3 layers over which equivalently through the Eigen structure of the channel, you are able to know these matrices UV, and you are able to actually understand from the designer point of view, this is my thing. These two systems are equivalent. Okay, these two systems become equivalent only when you do the pre-coding and the post-coding, pre-coding and receiver shaping. Transmitter may you do the pre-coding, and this receiver you do the shaping. Okay. So this is the most important thing that has to be known. And the condition number, this is actually, it's not condition, it is known as the condition number. Condition number of a matrix is defined as the ratio of the maximum singular value to the minimum singular value. Okay, for example, in this particular example, the maximum singular value is 1.4 and the minimum is 0.33. So 1.4 divided by 0.33, this number is known as the condition number of the channel. Now, ideally, this should be, if it is very large, that means the spread of the singular value is very large, then it will be one kind of channel. Okay. And if the spread is not very large, then it will be another kind of channel. The entire, so studying the statistical distribution of the singular values, that is a huge, you have to do that study if you want to design a system, MIMO system. And for my massive MIMO system, you have to be very particular about the statistical distribution of the singular values. Okay, this is known as the condition number. Okay, because if you don't know the condition number, it is no point in designing, because sometimes the channel will be such that it is not good for MIMO. MIMO laga ke bhi kuch, there will be no benefit. Why should you now spend on MIMO? So you have to, the designer has to first take the decision key, is the channel suitable for, it's not that for any channel you can design a MIMO. So how to understand whether a channel is suitable for applying MIMO? Best way is to find out the rank and the condition. If it is a full rank matrix, that means there is a lot of correlation. Okay, if the rank is less, means correlation is less. Okay, so now these are some of the properties that is important. For example, usually if you have polarized radio wave, spatial multiplexing does not bring any benefit. Even just imagine, even if you have a direct line of sight, but then no point in doing MIMO. So because the condition, number, rank, if those things are not suitable, then it is So so you have to understand that you have to do the do a proper study of the eigen structure of the channel before you actually go into the MIMO design. It is the radio channel which plays the decisive role with respect to the MIMO suitability. So before you actually start embarking on applying MIMO, so you sometimes for some indoors MIMO may be suitable, for some it may not be suitable. So basically what decides it is this matrix, this H decides. So only H ka jo hai, this is my H matrix. You have to take the SVD, study these vectors, and then you get to know what is happening. कैसे इसका singular values spread है, statistical properties. Lot of research papers you will find where they study the for different channels. They study the statistical distribution properties of the channel. ठीक है? So this is about your any questions till now? So as I was telling you, one important I don't know if you have heard about this algorithm. This is a very famous algorithm. Okay, this is the behavior of the MIMO channels eigen modes. This is now nothing to get confused about this. These eigen modes means these values, these eigen values. Eigen values here 1.4. These are known as the eigen values. So eigen mode 1, this is eigen mode 1. Eigen sigma 1 is eigen mode 1. This is eigen mode.
Hello. Madam. Hello, madam. Please unmute. Hello. Madam, please unmute. Debjani, madam, please unmute.
I was on mute.
Hi, you are muted. I don't know for some reason.
Okay.
Now
I did not do it anymore.
Okay.
So should I from where did we? I'm not able to understand. Then where should I start? Is it okay?
Huh.
Okay. So we had been talking about this. So this is the water filling algorithm. This is the water filling algorithm. Okay. So now we come to what we call the massive multi-user MIMO. We come to massive multi-user MIMO. In massive multi-user MIMO, what happens is that, as I please note what is happening over here, we are using, the base station is having antenna array, and here the receivers, it is a multi-user, means every user is going to have a single antenna, but the entire system is going to work as if whenever some signal is being sent, it is going to be sent, some beamforming kind of things are used, so that individually you direct the beam individually to each of the users. So it is also an NT cross NR kind of system, where NT will be the number of transmitting antennas on the base station, and here this will be the number of antennas on the user station. Here, please see that we were talking about the diversity. The diversity is going to be, somebody of you was telling how to get the effect of the diversity. Diversity will always be NT cross NR. So suppose you are used two transmitting antennas, 5 receiving antennas, 2 cross 5. So it is of the diversity order will be about 2 cross 5, that is going to be 10. But by degree of freedom will always be defined by the minimum of the NT antenna. So by degree of freedom, basically we mean, once again, this will basically decide the number of independent channels that you can actually have. Okay. So under favorable conditions, what happens is that when you have massive MIMO, the number of antennas become very large, and you have the channel vectors. But what we do is that I think we use a technique called beamforming. All of you must have heard of it. But then beamforming is once again related to pre-coding. Okay, usually as a part of pre-coding only, those different you have the beamforming weights are given to the different antennas, so that the antenna gains become actually in proportionate to the pre-coding weight vector. So pre-coding is very much related with beamforming. In some books and some papers, they use the same term for beamforming and pre-coding, although there is slight difference. Beamforming is actually a software, signal processing. Okay, whereas your pre-coding of course is signal processing, but beamforming is mostly about the hardware part, where physically the antennas, the arrays are formed, and they are able to give different gains to the different beams. Okay, we'll see to this. Any questions up till here? Okay, so massive MIMO. Now let us come to the massive MIMO part. I want to just quickly finish the main point so that we can have a quick discussion about the entire thing. So massive MIMO, you have definitely a large number of base station antenna. Please note that the massiveness is with respect to the number of antennas, but not size. In fact, size is quite small. Okay, so implementing hundreds of antenna definitely does not mean a huge physical size. The size continues to remain the same. But then how do we do it? This is where the band becomes important. Okay, if you are working on a very high frequency band, then the size is definitely going to be less. That is what happens when you integrate millimeter wave with MIMO. Now please call after some time. Huh? Okay, sorry. So implementing hundreds of antenna does not imply a huge physical size. Then we also talked about something called uncorrelated noise, small scale fading, and the transmitted energy per bit. So here, with the help of MIMO, what we can do is you'll find that we have got a tremendous control over the fading, noise, and even your bit error. Okay, so that the reliability of things can improve to a very large extent, because what happens is that you are having a very good system. Entire feedback system is working so well, and you are able to compensate, almost you get zero error. Okay, and that is why you have the 5G quality and all is supposed to be very good. So basically the idea is definitely channel estimation, and then doing the pre-coding thing, which is actually compensating whatever is the problem that is going to come, change it into a simple AWGN type of independent channels, where you can just do the equalization just by division only, or multiplication and division only can give you the equalization. Okay, thermal noise, as I told you, it's almost become gets averaged out. Interference, alignment, interference, cancellation. So little bit of signal processing can help you to achieve so many things. But please remember, we already know the match filter and pre-coding, so they can be used to the MIMO advantages of diversity and multiplexing. So at every point, what happens is that you will find that the main important role is that of pre-coding, which is actually taking care of many of the advantages. Now, massive MIMO the pre-coding becomes a little bit challenging. Okay, of course, that the massive MIMO gives you, I mean, those of you who have already used 5G. Okay, I mean, they tell, I mean, it's tremendously fast. Your latency is the time it takes for the by the time you transmit the signal and you receive it back. So most of the advantages of massive MIMO is tremendous if you get. And at the heart of it is that you have to have a proper knowledge of the channel. Now we come to the next part of it that we're talking about. With massive MIMO, the other aspect, the other two important technology that is becoming very important for 5G is your, other than massive MIMO, it is my millimeter wave. What happens in millimeter wave? Millimeter wave is nothing very, new. Its only thing is that we are going higher up in the electromagnetic spectrum. So we are moving into the, what is the typical millimeter wave band? That means it's 30 gigahertz to 300 gigahertz. So when we go from 30 gigahertz to 300 gigahertz, definitely you will get high data rate communication. And most of your, these days we are talking about the self-driving vehicles, autonomous vehicles. So for autonomous vehicles, I think this range of frequencies, a very high data rate required. So normally millimeter wave frequencies has been found to be very, very suitable for this range, self-driving vehicles. A lot of work is going on autonomous vehicles. Then the other one is your IoT. Your IoT also, you require latency. Latency means that the time should not be too much. Okay, the real time makes working. So if it is working in real time, the latency requirements are very less. So latency requirement less can only happen only when you have a very high data rate, and there once again millimeter wave can be a big shot over there. Okay, most of the things, as I was telling you, in millimeter wave, this getting this steerable directional antenna is just showing you this figure. This is exactly what happens. You can get steerable beamforming with very, very focused, just like laser beams. You can almost focus your, so even if there are obstructions, your signal is going to reach this particular. So you get this very highly, what you call directional steerable beams that you can use between the base station and mobile station. The millimeter waves can also be used for backhauling. Backhauling means it is acting as a intermediate unit between your core network and the base station. Okay, let us see. And what most important thing is that it is going to be a replacement for your fiber optic links, because fiber optic links is also giving you very high bandwidth, isn't it? Now the range of bandwidth that you get in fiber optic links, almost close to that you can get in millimeter waves. Only thing is that it's wireless, but here you have to use lay optic links. So always wireless is better than your wired. Okay? The deployment is much easier. So millimeter wave is the main advantage. I think all of us can very well understand, because it's very high frequency. You get good scope of high bandwidth, and then some of the latest applications, they are very, very much suited for millimeter wave. Okay, people have been already deploying these, especially in autonomous vehicles and IoT. So I was talking about this backhaul thing. So in your normal 4G, this is my normal 4G. What is the difference when you have a millimeter wave backhaul? Okay, millimeter wave backhaul means this is my mobile, this is my base station. This is my directly your mobile is getting connected to the base station. This is my 4G. Now what you have is that these are the small cells. What happens in the when you are using it as a backhaul? Backhaul means you can use millimeter wave small cells. When you use small cells, you use small antennas are there. Okay, these access points. So these are going to act as a, so your mobile is going to get connected to the access point. So naturally your quality of transmission will be much better. So your mobile is now not connected directly to the base station, only to the access point, and this access point is connected to the base station. This is what we mean by the backhaul. And this small cells the small cell concept, picocell, femtocell, and all, millimeter wave frequencies is proving to be a very good interface. Okay. So current usage, you can see currently practically you have, these are the bands that millimeter wave uses: 28 to 38 gigahertz, 57 to 64, 28, 38 gigahertz. Mein dekho, just look at the bandwidth that is available in all these. Just have a look at the bandwidth. In the 28 to 38 gigahertz, you get a bandwidth close to 500. If 57 to 64 mein, you get 2 gigahertz bandwidth. In 70 to 90, you get 4 gigahertz bandwidth. This is nothing compared to our mobiles, the 4G mobiles. 4G mobiles which working in the sub gigahertz bands. We have sub gigahertz. We have broadly two bands both there, sub gigahertz and more than 6 gigahertz. Because the channel properties changes after 6 gigahertz. Below 6 gigahertz, some channel models are effective. After 6 gigahertz, they are difficult type of channel models. And look at the bandwidths, only 50 megahertz. Just can you imagine 50 megahertz ke comparison with 500 to 4, they were tremendous. So this and this large bandwidth is also gives us the quality is also improving, because I think you know ISI and frequency selective fading and all these problems in wireless communication. This can be the moment you have large bandwidth, you know, the coherence bandwidth, say your bandwidth is large. So, but what happens is that these problems will further increase, isn't it? Because coherence bandwidth now usually is small, and then now your bandwidth is large. But then, how to handle it? This is again when you mix it with MIMO, a lot of things can actually be improved. So the overall take is that till now that we have studied is definitely MIMO we all understand, massive MIMO we all know, we saw millimeter wave. There are benefits, but new benefits are there, but new problems are there. Lot of problems are there. Biggest problem is my power consumption. Okay, because whenever I'm moving to millimeter wave, you're using those A to D converters and DAC converters, and then the power consumption is too high. And I told you in the beginning of the lecture itself that we cannot afford to have a large power. Okay, and another thing is that your coherence time and I think those of you have studied wireless communication, you know that smaller coherence time should always be large. Coherence time large means the channel is going to be behave like a time invariant system. If the coherence time is small, it becomes the time varying property, mobility those things becomes very complicated, and you have to frequently estimate the channel. Okay, but if your coherence time is large, then you don't need to estimate the channel frequently. But this is one of the problems that millimeter wave channel may what happens because frequency is high, the coherence time is high. Another problem is that most of your channel models are all I mean they will not work in millimeter wave. The Rayleigh, Raytheon, Nakagami, the conventional fading models जो हम लोग use करते हैं in your simulation or studying, designing, they fail. They fail at the millimeter wave. So these days you have FPR, then TWDP, and kappa, gamma, mu. Some 3-4 channel models are coming which are specific for the millimeter wave. One more important thing is that there's too much of disturbance, you know, atmospheric absorption, human bodies, you know, even human bodies, they affect the millimeter wave. So they are going to absorb some of the waves. So what happens is that the propagation, attenuation, loss, they are too much. As I told you, you have benefits, but then problems are there. Another big problem is that it is sensitivity to rain. You know, when it is raining hard, if it is raining hard, your signal strength will degrade because rainwater, it absorbs the millimeter waves. And then all these things, people are making huge studies on these areas. So depending on how much you are away from the base station, you may have problems. Now, the moment I combine the millimeter wave with massive MIMO, what happens is that then they complement each other. That means each of them can overcome some of the drawbacks. For example, one of the drawbacks of the millimeter wave was the channel attenuation and loss. Now that can be affected by how? With the help of what you call is the spectral efficiency. When you use massive MIMO, what will happen? It can give huge antenna array gain. So what will happen is that even if your propagation path loss is there, so it will help to compensate that. It's something like holding hands. It's a very good marriage partner. So when the massive MIMO meets the millimeter wave, both can actually help each other. The other one is that MIMO needs large number of antennas. But the large of antennas, how to fit them into a small antenna array? Physical size cannot be very large. But because of the millimeter wave range is small, so they can be actually very easy to deploy. So these are the two mutually beneficial ways in millimeter wave can help massive MIMO, and massive MIMO can help millimeter wave. Massive MIMO can give rise to beamforming. So even if there is problem in this propagation path loss and channel model and all, and your frequency selectivities, those things can be affected. Okay, so there is a huge potential of MIMO in the millimeter wave band. You'll find a lot of good papers. You can just read them to have an idea. So small wavelengths, they are facilitating the massive MIMO because you can use thousands and hundreds of, even within a few centimeters, you can accommodate hundreds of antennas. Okay. Then, as I told you, beamforming is a very important application, which is with the help of pre-coding, you can give the proper assignment of beamforming. That actually compensates for the power loss. Okay. Beamforming is one of the biggest advantage of MIMO that millimeter wave can actually take care to remove its limitation. So, but still, both MIMO and millimeter wave has got huge implementation and operational cost. Okay, so still in the research area, a lot of research is going on. Okay, a lot of challenges in millimeter massive MIMO. Those of you are working in the newly, you can actually study. Just a minute. Okay. Okay. So challenges. So there are many problems. So one of the main problem is that the high frequency and the large of antennas, they result in high path loss and severe interference. But then, as I told you, MIMO you have various signal processing techniques that can actually cancel the interference and all those things. Okay, improving spectral efficiency. This is one of the biggest research goal for 6G communication. High energy consumption, and this is extremely, because when power consumption is more, then naturally a lot of other cost complexity comes. So these are the kind of research areas in which people are trying to make it more energy efficient, more spectral efficient, as well as more cost efficient. Okay, pre-coding is a very important part of it. So if you have a good pre-coding technique, okay, normally you have analog pre-coding and you have digital pre-coding. What happens is that in digital pre-coding, you have to have jitna number of antennas hai, utna number of RF chains lagta hai. So it becomes very hardware wise, it becomes very complex, but it gives very good spectral efficiency. Analog mein kya hota hai? Analog mein you have one RF chain, but then you don't get very good spectral efficiency. So there are a lot of issues. I'm just trying to tell you some of the research challenges on which people are working. So power consumption, you can have a typical idea about the power consumption at millimeter wave compared to microwave. Can you see power consumption at millimeter wave is typically around 250 milliwatts, whereas it is in microwave range, micro frequency is 30 milliwatts. So can you imagine the amount of power loss that is happening? So power loss is a big issue because see, millimeter wave में अगर massive MIMO work करता है तो pre-coding करने के समय I need pre-coding में I have to have so many RF chains. The hardware of the pre-coding is becoming very, very costly. So these are some of the areas in which people are doing. So I was telling you, beamforming is one of the areas that is closely, beamforming is nothing but little bit related to pre-coding. Okay, it's not exactly pre-coding, but some books they also sell it the same thing, because both are actually happening together with the help of the channel Eigen structure only it is happening. So beamforming is a frequency management technique in which either the base station or mobile station is making use of the various antennas to transmit information at the same time, but then they are assigning the array gains in a different way. Okay, massive MIMO is purely hardware. Beamforming is a mathematical algorithm which is a part of massive MIMO. So whenever massive MIMO is there, definitely pre-coding will be there. With the help of pre-coding, you can do the beamforming. And beamforming helps us to solve some of the problems of millimeter wave that we were talking about. Okay. And what we do is that beamforming algorithm itself is a very complex signal processing. You need to do the channel estimation. Okay, ideal path it has to follow. Then we have to find out how much efficiency can be increased. So and then you can control the SNR and overall network capacity is improved. So this is a very integrated, very beautiful mathematics working for you, which helps us in a closed feedback loop to control the channel. Although you don't have any control over the channel, this entire thing, just with the help of some signal processing, you are able to do the entire thing. So you are able to understand the SNR, you are able to do the power efficiency, power allocation, spectral efficiency, entire thing becomes under control. Now, the moment I was telling you, when you have millimeter massive MIMO, another very important thing that comes is the sparsity. Sparsity means this is a very big problem of the millimeter wave channels. You know, millimeter wave channels the number of multipath is very less. It is not like the sub-gigahertz. The millimeter wave range frequencies typically will be about 20 gigahertz and beyond that. Okay, and I told you 6 gigahertz is a limit. After 6 gigahertz, the channel model itself changes. And then can you imagine what will happen to the channel matrix? The channel matrix will become sparse. What is meaning of sparsity is a mathematical term. Sparse is where most of the entries will be zero or very low. Now, this is a very serious problem, is one of the very strong research areas on which people are working. This is once again our signal processing area. So you can have, I'm not going to go into detail, temporal sparsity bhi hota hai, spatial sparsity bhi hota hai, okay? Temporal sparsity where you have a lot of zeros, in between you have nothing. So this is very bad. You know, the Eigen value actually gets affected. So the Eigen structure of the channel becomes very, very challenging. And then there are special ways to handle entire processes for this. Okay. So large scale MIMO, this is nothing but your massive MIMO. These are 4 things that normally does. Everywhere I need to know the Eigen structure of this. Beamforming, decoding, interference alignment, data detection. In चारों process के लिए we need the Eigen structure of the channel. Okay, that we have been talking about. Okay. Out of this, as I told you, beamforming is the most important one because millimeter wave will not work without beamforming because it has got its channel conditions are very, very bad. Okay. So what we do is that it's a technique we try to match. This is where we had started. Okay. It's a technique which can match my transmit and receive signal to the propagation channel. It's a very, very wonderful way in which you can actually do this matching. At the receiver, you are coherently combining them. Okay, and this once again results in increased signal power. This is a tremendous advantage. So that's why we call the beamforming gain. Okay, and this is where you can take care of the power loss. Because I was telling you in millimeter wave, mein power loss bhi hota hai, and the other types of losses are also there. So power loss is usually compensated with beamforming gain. You use the SVD, singular value decomposition. Both the beams can be formed at the receiver and the transmitter. But normally you do it only on one side. Okay, so mostly you will find that these days when 5G will be introduced, most of your stadiums or malls or where you have a lot of users. Okay, because it's going to work. All the users are going to act as a number of everyone is having a single antenna. Overall, it's going to be a massive MIMO system, and you will have beamforming transmitters. So this is going to be my massive MIMO system. Beamforming transmitter. So I think you have analog and digital beamforming. This I'll skip. I think there are because this is a serious problem. Analog and digital. What happens is that analog is having some advantage, digital is having some advantage. So what people do is that they use a hybrid. Kuch portion analog karte hain, kuch digital. Okay. So let us just come to the end. You must be all tired or listening to me since 1.5 hours close to. Okay. So the new era where you are actually the things that we have discussed is individually we have discussed what is MIMO, what is massive MIMO. Individually, what is millimeter wave propagation? What happens when you have them together? As we talk that one millimeter wave, they can be used. They have been being used. Okay, but earlier what happens was that I was telling you that the power consumption was a big issue. But these days, semiconductors industry have actually manufacturing lot low power semiconductors and all. So there, what happens is that this again millimeter waves will be very much in vogue. So high bandwidth, high throughput once again, but then small antenna size. So moment I'm using millimeter wave, this is where I'm able to get. So this is beautifully helping each other. Okay, one is helping each other. Okay, so front end system can have a large number of antennas using small size, and then they use what you call the beamforming technique. And as I've told you, the beamforming you do it usually in the hybrid mode. Okay, little bit up because digital beamforming is hard. It gives you a lot of multiplexing gain, but then at the cost of tremendous amount of hardware. Okay, that is not always possible in massive MIMO. Okay, so this is and basically at the base of it, we discussed about the Eigen structure of the channel. The entire performance depends on how well you know the structure of the channel. And then a simple technique we talked about, singular value decomposition of the channel, which you are factorizing the channel into 3 important matrices, and then you are using those matrices, one of them at the transmitter, the other at the receiver, so that overall you can integrate and form what you call much more tractable matrix that will help you in designing and simulation. Yes, can we have a little bit of questions if you have? I don't know if I managed that. 10 minutes we have, I think.
Yes, madam. Any questions from participant side? Namrata Chobe. Yeah.
Yes, please, Namrata, please. Hello, Namrata.
Hello.
Hello. There is no question from my side. I just put my hand just because at that time ma'am's voice is not coming.
Okay. So anybody wants to have some interaction, we are free.
Ma'am, am I audible?
Yes, Ifra.
Ma'am, you said that for a full rank matrix, there is a lot of correlation. That's what you said. So, ma'am, like for a full rank matrix, ma'am, how can you explain that? Because
see, correlation, see, this will depend on the, see, what normally happens is that when you have very rich scattering, that when the environment is very, very scattered, I mean, you have too many objects. That normally happens in our normal. See, this is the difference between millimeter wave and my normal channel. See, the normal, we are working now on the sub 6 gigahertz, below 6 gigahertz range. Most of our mobiles are working there. So in that range, the scattering is very rich. Mostly, what is the fading? It is Rayleigh. So there, the correlation is not going to be very strong. Okay, so that it is possible to get the independent matrices. But what happens if the correlation is not there? Okay, or if, see, there can be two things. So it is very difficult to tell. You have to study the correlation property of the channel. How do you find out the correlation property of the channel? That can be found out from the H matrix itself. Okay, if you find the autocorrelation function of the channel matrix, from there you can actually find out the correlation of individual. So correlation, do you think correlation is good or correlation is bad?
ma'am, if the entries are linearly independent,
entries are not independent. See, try to understand this. Entries are not independent. We are trying to realize the equivalence. That suppose what I am trying, that's what I told you. See, channel is not in your control. Okay, you are traveling from one car is traveling from one end to the other. The road is not in your control. Okay, so what is in your control is that you can do something to the car. So if you know the road is very bumpy, so you can put some coating in your tires, and also that the tires don't get affected. So something like that here we are doing. We are not. You cannot change the channel from a correlated to uncorrelated. Channel, whatever, if it is correlated, it will be correlated only. Whatever is, so that is where your Eigen structure of the channel will give you an idea. If you do the SVD, so if you do the SVD, take the rank of the matrix, see the condition number, see the correlation properties. So when you do those things, okay, then only, and because in your MIMO capacity equation also you will get the correlation of the channel. Now, this is what happens in your millimeter wave channel. What happens is that the channel is very sparse. Okay, so and it is so sparse, then now the sparsity creates other type of problems. What happens is that when you don't have, because what happens is that in between there are you will not get the signal. That is one more important thing that happens in the millimeter wave. When the signals are not too correlated, what will happen? There are not too many scatterers. So because they are getting absorbed, at higher frequencies, what is happening? The electromagnetic waves are getting absorbed by different objects. So what will happen? The scattering will be less. If the scattering is less, what will happen? Your range will automatically get less. Okay. Now the correlation, once again, we have to study. That is where the research is going on. Very few measurement studies have started on the millimeter wave. Most of the sub gigahertz range have been studied. So they are very good for MIMO, for low order MIMO systems, 2x2, 4x4. We have also two antennas, 4 antennas like that. Okay. But then moment we go for massive MIMO, people have still, a massive MIMO will not work with sub gigahertz. We have to go with millimeter wave. And then so many things have to be studied. You have to study the correlation property. You have to do the SVD and then see how much of the correlation. So H into H transpose, if you do, that becomes a correlation matrix. Okay, covariance matrix. So from the covariance matrix, you will get an idea about the how much of correlation is there. That is equivalent to, and then if you do the eigenvalue decomposition, you get nothing but the singular values. Okay, that is why that was the basis of my talk for the entire day. That how to use the significance of the Eigen structure of the chart. Ifra, is the question clear?
Yes, ma'am, I got it. From the H matrix only, from the channel matrix only, we have to calculate the correlation.
Yes, it is H into H transpose. If you do, you get the covariance matrix. That will give you the correlation. Okay. Now, it is just a mathematical interpretation that if I do that pre-coding and post-processing, then equivalently you are able to interpret it. That's the thing. You cannot change the channel. Channel jaisa hai, waise hi hai.
Okay, ma'am. Thank you, ma'am.